Welcome to This Explainer. Today, we're tackling a massive question. How do we actually give artificial intelligence a functioning, reliable brain with long-term memory? Look, if you've been working with large language models lately, you already know they are incredibly smart. But their memory, well, it leaves a lot to be desired. Today, we're going to demystify the exact architecture that's changing all of that, using the latest insights on vector databases, graph RAG, and agent memory.
Okay, here's our roadmap for today. We'll start by fixing AI's memory problem, then introduce the vector database, compare native versus extended databases, add context with GraphRag, and finally, look at building long-term agent memory. Let's get right into it.
Section 1. Fixing AI's memory problem, curing amnesia and hallucinations. So, have you ever wondered why an AI, one that has literally read the entire internet, can suddenly just forget what you asked it exactly 3 prompts ago? It's incredibly frustrating for developers and users alike. You spend all this time building up context in a chat, and out of nowhere, the model just drops the thread entirely. Well, it basically boils down to 2 distinct conditions. First up is oblivion. Think of this as goldfish-like memory loss where the model just loses the context over multiple queries. The second, and yeah, this one's definitely more dangerous, is hallucinations. That's when the model confidently makes things up, generating completely factually incorrect data just to fill in the gaps of what it doesn't know.
The fix here isn't just throwing more data at it or training bigger models. Actually, scratch that. It's a completely architectural fix. By attaching a dedicated long-term memory system to the model, we can feed it real-time facts and wipe out these issues. This allows a generalized LLM to use highly domain-specific data, and it stops the model from becoming totally outdated the exact second its initial training ends. This, right here, is the foundation of RAG, or Retrieval Augmented Generation.
Moving to Section 2. Enter the vector database, the engine of AI memory. So what is the actual engine driving all this? Well, in the modern AI world, data, whether it's an image, a block of text, audio, or a video, is mathematically converted into vectors. The catch? Traditional relational or NoSQL databases just aren't built to directly store or index this kind of unstructured vectorized data. Even NoSQL databases force these strict trade-offs between consistency and availability that honestly just don't work for AI. We actually need to introduce a new kind of relaxation into the system. That relaxation means accepting an approximate result. Imagine trying to find a friend in a massive stadium. Instead of checking every single person's ID, you just ask around for people who look similar. That's exactly what Approximate Nearest Neighbor Search, or ANNS, does. To avoid checking a million vectors one by one, the database picks a random entry point, gathers similar vectors, and gives you an approximate result with absolutely blazing fast performance.
Under the hood, developers are using some pretty intense indexing techniques to keep this all organized. Things like HNSW, locality-sensitive hashing, and KD trees. You don't need a math degree to get it. Just think of them as highly optimized filing cabinets. When a query comes in, the database uses complex distance metrics like cosine or Euclidean distance to instantly calculate similarity and grab the exact memory the AI needs without skipping a beat.
Section 3. Native versus extended databases, mapping the landscape.
Okay, let's look at the actual tools developers are using out in the wild. You've essentially got 2 camps emerging. On one side, native vector databases like Weaviate, FAS, Qdrunt, and Milvus, which were built entirely around vectors from day one. On the other side, you've got the familiar heavyweights, Postgres, Cassandra, Mongo, Redis, that have basically bolted on vector extensions to handle these new AI workloads.
If you are evaluating a database for your AI stack, this is your ultimate checklist, straight from our source material. You've got to ask, is it native or extended, exact or approximate search? Can it handle hybrid searches? What about inserts, updates, RAM versus disk storage, and hardware acceleration? Your answers to these questions absolutely dictate the kind of performance you're going to get.
Take Weaviate, for example. It is a fantastic native solution that passes those checks with flying colors. It uses that HNSW graph index we talked about earlier to pull off some incredibly complex, approximate hybrid searches. It's practically tailor-made for the kind of speed and scale that today's LLMs demand.
Which brings us to Section 4, adding context with GraphRag, the network.
Now, vectors are amazing for finding similar concepts, but here's the thing. Humans don't just think in similarities, we think in relationships.
Enter the knowledge graph. This is tech that encodes how concepts relate to one another, along with basic common sense knowledge. And honestly, it's not even new. It boasts a rich history spanning 30 to 40 years.
When you combine those lightning-fast vector searches with these historic knowledge graphs, you get a phenomenally powerful tool called GraphRAG. Tools like the Neo4j Vector DB do this brilliantly in 2 steps. First, it uses vector search to quickly pinpoint relevant data nodes. Then, it uses all those connected entities and relationships to build out a deeply comprehensive context for the LLM. It's literally the difference between pulling a random fact and truly understanding an entire topic's ecosystem.
And finally, Section 5, Building Long-Term Agent Memory, the Future.
So, moving beyond simple chatbots, how do we build long-term memory for autonomous AI agents? Right now, chat interfaces just save your prior conversations and shove them back into the model's context window. But what if you've been working with this agent for a whole year? As our source bluntly points out, passing every single session from last year into the prompt every single time is just completely ridiculous.
We clearly need memory techniques that can intelligently retain and, just as importantly, discard data. To do this right, intelligent agent memory needs 3 distinct dimensions: chronology, relationship, and tiered memory. Let's break those down.
First up is chronology. Facts evolve over time, right? Take the Cricket World Cup. India won it in 2011, which is a fact. But if you ask an AI who is the World Cup winner, it has to understand the timeline, because across all the tournaments, that concept of a winner has at least 11 different versions depending on the year you're looking at.
The second dimension is relationship. But let's jump right into the third dimension, tiered memory, because it's a real game changer. Think about it. You know a ton of geography, history, and math, right? But how much of that do you actually use when writing a simple JIRA ticket at work? An AI needs tiered memory so it doesn't waste compute power pulling up 18th century geography when you just need a software bug updated. It determines exactly what data is relevant for the task at hand.
Because building this is so complex, developers are actually splitting the workload across specialized tools in the ecosystem. XAM is a tool that is laser-focused on handling that chronology piece. Cogni steps in to map out the relationships, and Leda takes on that tiered memory, figuring out retention limits, how to modularize data, and exactly where it should live.
So as we look to the future and build the next generation of digital brains, it all boils down to one massive question: how much data truly deserves immediate attention? We've got the vector databases for storage and GraphRAG for mapping the context, but true intelligence for both humans and machines isn't just about remembering everything. It's about knowing exactly what matters right now. Thank you for tuning into this explainer, and I hope it helped untangle the incredibly cool architecture behind AI memory.